a neuroscience lab, studying emotional learning and memory. During my time in this lab, I would spend weeks collecting data for my experiments. And while I love running experiments, manually collecting data took time, and I'm a bit of an impatient person. And that's when I discovered neural networks, a type of machine learning algorithm inspired by how the brain functions. From then on, I was hooked on AI and wanted to create more machines capable of human-like intelligence. Hi, I'm Sadie St. Lawrence, founder of Women in Data, principal at SSL Innovations, and technology educator. In my course, we'll begin with an overview of AI. Next, we'll look at some popular tools and their uses. We'll get hands-on with high-level machine learning techniques and wrap up by discussing project life cycles, ethics, and bias. So if you're ready to take a deep dive into deep learning, then let's jump in. Things like self-driving cars, personalized recommendations, and digital assistants like Alexa or even ChatGPT have jumped off the pages of science fiction and have become a part of everyday life. This new and ever-changing world could only be a reality thanks to artificial intelligence and machine learning. In this video, I'm going to provide an overview of AI and machine learning so you understand the basics of these technologies. So what is artificial intelligence? Artificial intelligence, or AI, refers to a broad field of science focused on building smart machines capable of human-like intelligence. The key idea is that by studying how the human brain works, we can engineer computer systems to mimic human cognitive functions like problem solving, pattern recognition, and even decision making. But because AI encapsulates several concepts into one, it can get confusing when the term is used to discuss its more commonly used subfields. For example, individuals may refer to AI when discussing robotics and even robotic process automation, RPA. But for this course, and as data professionals, we're most interested in algorithms and the networks that power AI, which we refer to as machine learning. Machine learning is a subset of AI focused on algorithms that can learn from data. And as data professionals, coming into this class, you have the key understanding of working with data, which is just what these algorithms do to create AI. A basic example of machine learning and how these algorithms can mimic human intelligence is the chess-playing computer Deep Blue by IBM. Deep Blue can strategize moves and defeat human players. The software is intelligent because it can explore potential future moves just like a human chess player. The algorithm learns by identifying patterns and relationships in the data in order to make predictions or decisions without explicitly programming. For example, machine learning powers the recommendation engines used by Netflix and Amazon to suggest new movies or products based on your viewing and purchase history. The more data they gather, the better their recommendations become. Though the term is over 60 years old, AI and ML have taken off in this past decade due to new techniques like deep learning and the growth in computing power and data. Deep learning uses neural networks modeled after the human brain to process huge data sets and drive major leaps in capabilities like large language models, computer vision, and natural language processing. For example, deep learning enables a facial recognition algorithm to go from detecting faces to accurately identifying who a person is by analyzing thousands or even millions of images. The more data it trains on, the more accurate it becomes. AI and the rise of deep learning has enabled major advances in both AI and ML. And this has led to the rapid evolution of new technologies and innovative applications. And as a discipline, it will only continue to grow in complexity and prevalence. After this video, I challenge you to think of at least 2 examples from your daily life that involve artificial intelligence or machine learning. Self-driving cars, personalized medicine, and even those viral AI art generators. But not all machine learning works the same way. In the previous video, we discussed how AI can be confusing because of the main term it encapsulates. While the basics of AI is machine learning, in this video, we're going to break that down even further into the three types: supervised learning, unsupervised learning, and reinforcement learning. Knowing the strengths of each will help you leverage machine learning more effectively in your own projects. Let's start with the most common one, supervised learning. In supervised learning, algorithms are trained on labeled datasets, meaning the data has been pre-tagged with the right answers. For example, you can feed an image recognition algorithm hundreds of labeled cat and dog photos, so it learns to spot the visual patterns for each. It uses this human-labeled data to build a predictive model. Supervised machine learning is a very powerful tool, but as you can imagine, not all data comes naturally labeled with the answer. Therefore, we either need to manually label the data or see if another technique is suitable for the job. On the other hand, unsupervised learning doesn't need labeled data. The algorithms are given raw, messy data and left to find patterns and groupings on their own without any human guidance. A good example is a clustering algorithm that can segment customers into personas based on similarities that it detects between data points. This allows for the discovery of completely new insights. One of my favorite models that I built was a K-means clustering model for a marketing team. This team was interested in creating more specialized marketing materials for their customers, but didn't know how to categorize the customers into like-minded segments. Hence, the perfect use case for unsupervised learning. Now, reinforcement learning works more like how we as humans do, and it learns through trial, error, and practice. The algorithm interacts with an environment, constantly trying different actions and receiving feedback on whether that action gets it closer to its goal. Like a chess engine playing against itself, it reinforces strategies that lead to wins and discards those that fail. This is how an AI like DeepMind mastered chess without training on human games. To quickly recap, supervised learning needs labeled data, unsupervised learning finds hidden insights, and reinforcement learning uses trial and error. These are the three areas that are the current backbone of machine learning. But that could quickly change as the field matures. Regardless, be sure to clearly understand these different types of machine learning, because focusing on the right approach for your needs will ensure you successfully leverage the power of machine learning. After watching this video, I challenge you to jot down one potential application idea for each ML type. This will help you cement your understanding, but also help you start to test how to match a use case with a type of machine learning. It can be overwhelming. The key to diving into AI and machine learning is less about the tools you use and more about your approach and specific use case. But hey, knowing where to start is crucial. In this video, we'll explore 5 indispensable AI and ML tools. Note, I'm assuming you're comfortable with languages like Python and SQL. If you're not, do yourself a favor and get a strong Python foundation before diving into these awesome tools. So let's take a look at the first tool, Scikit-learn, the starter pack for machine learning in Python. Why should you care about Scikit-learn? Well, think customer segmentation or predicting house prices. Scikit-learn is fantastic for classical ML algorithms like random forests, SVMs, and K-mean clustering. If you don't recognize some of these fancy terms, just think of them as tools that output predictive analysis from large datasets and other tools that check the outputs for accuracy. Scikit-learn's library makes model training a breeze. Plus, it offers excellent tools for model evaluation, hyperparameter tuning, and feature selection. Next up is PyTorch, the deep learning maverick. If you're interested in advanced projects like autonomous driving, PyTorch is your friend. Known for its flexibility and speed, it lets you evaluate code line by line, making it perfect for quick iterations. Whether you're a newbie or a pro, its dynamic computation graph is a lifesaver for debugging. Keras, making neural networks a piece of cake. Ever wanted to dabble in image or voice recognition? Keras is designed for these kinds of neural network tasks. It's high-level API that can run on top of TensorFlow or PyTorch and simplifies building complex neural network architectures. Ideal for fast prototyping and trying out multiple models. Fourth is XGBoost, your go-to for boosted trees. Let's say you're working on a recommendation engine. For that, you'll want something built for speed and performance. Enter XGBoost. It's designed for boosted tree algorithms that combine multiple decision trees for accurate results. XGBoost can handle big data and still perform exceptionally well. And finally, Hugging Face, the NLP wizard. For any text-based applications like chatbots or sentiment analysis, look no further than Hugging Face. Its Transformers library offers thousands of pre-trained models like BERT and GPT-2 that you can leverage for various NLP tasks. Look, there are a gazillion AI and ML tools out there, but mastering these 5 will set you up nicely. If you're starting, make Python your playground and try out scikit-learn or PyTorch based on your project needs. Once you're comfortable, branch out to other tools. Your challenge is to pick one of these tools and start a mini project. Share your experience and results in the comments or in our community forum. Let's learn across virtually every industry. But what does applied AI actually look like? Well, in this video, we'll look at 3 real-world examples to showcase how organizations are using AI to solve problems and improve processes. Understanding current use cases will spark ideas for how you can apply AI in your own role. Let's start with healthcare, where AI is being used to analyze medical scans and detect diseases earlier and more accurately. Using convolutional neural networks built with PyTorch or TensorFlow, AI systems can pinpoint signs of cancer, fractures, and other issues by identifying visual patterns in scans. One company, Analytic, has a deep learning algorithm that interprets CT scans 50 times faster than a radiologist with 99% accuracy. A potential game changer for screening and treatment. Next up is business, where AI chatbots and virtual agents are transforming customer service through natural language processing. Tools like Hugging Face and natural language APIs enable bots to understand customer questions, then respond with relevant info. 1-800-Flowers uses IBM Watson to provide gift suggestions based on occasion, answer questions, and even process orders. Manufacturing is another area seeing gains. Computer vision AI can automate quality control on assembly lines, using image recognition and deep learning and more consistently than human inspectors. Nissan uses this visual AI at many of its plants to analyze thousands of images and spot microscopic manufacturing defects. As you can see, the applications for AI are vast, from healthcare to business to manufacturing. And new innovations are happening every day as companies find more ways to infuse AI into products and processes. After watching, discuss with a colleague or friend an idea that you have for an AI application in your field and get their feedback. Brainstorming use cases is a great way to expand your thinking on this transformative potential of AI. The LinkedIn network is a great way to connect and learn from others in the field. So don't be shy. Post and share your ideas today. Because who knows, you might come up with the best new use case for AI or break for building effective AI systems. In this video, we'll explore the key data types and sources to power your AI and machine learning projects. Understanding your options will help you build robust data pipelines. Let's start with the two main data formats, structured and unstructured. Structured data has a predefined model like rows and columns in it or a SQL database. If you are a data professional, most likely you have experience working with SQL databases. This includes most customer info, product specs, operational metrics, and even quantitative data. Structured data is crucial for training machine learning algorithms. The rigid structure allows the algorithms to map input data to outcomes for tasks like prediction, forecasting, and recommendations. For structured data, SQL databases are particularly important. SQL enables efficient querying, cleansing, and analysis of large datasets. Most organizations will leverage SQL alongside tools like Python and Pandas when prepping data for ML. When it comes to volume, more data is better for your machine learning. And you'll see why in the next few lessons as we discuss splitting our data from training and testing, so please keep that in mind. You often need thousands or millions of data points for accurate training, especially with deep neural networks. Conversely, unstructured data has no defined model, like images, video, audio, or text. This is common for computer vision and NLP tasks. The algorithm extracts relevant patterns from pixels and words instead of columns values. Now let's talk about the sources. Internal data like sales numbers, customer info, web traffic logs are a great starting point. But you may need external data too. Scraping public websites can expand your data sets if done ethically. There are also many curated public data sets on sites like Kaggle and or open data portals from your local government for benchmarking models. Synthetic data is another option. This is artificially generated to match patterns in real data. It's useful for augmenting small data sets or anonymizing sensitive data. If you need niche, hand-labeled data, you can either do it yourself, which is time-consuming, or use one of the many contracting services for custom data annotation and tagging. Blending data from multiple internal, external, public, and synthetic sources is often best. The key is picking your sources suited to your data format, volume needs, and end goals. As a data professional, you most likely have experience working with one or all of these types of data sources. Let's say you have experience working with structured data, then maybe a fun use case would be to try something with computer vision using unstructured data. Either sticking with what you know or trying something new is a good option. Either way, remember to have fun in any machine learning project. This provides the initial insights into the data set you're working with. Before modifying or even cleaning the data, understanding your data is paramount. Think of it as an orientation phase. You wouldn't embark on a long journey without first surveying the landscape. Skipping EDA could lead to flawed analysis. It involves a variety of techniques and approaches. So let's explore some. Descriptive statistics like mean, median, standard deviation, and quartiles provide a numerical summary of your data. These measures allow you to grasp the central tendencies, dispersions, and even the shape of each variable. For example, knowing the average age in a dataset can set the stage for further analysis on age-related trends. Data visualization techniques such as histograms, scatter plots, and box plots come in handy here. Imagine you're looking at a scatter plot of customer age versus spending. If you notice a trend where spending increases with age, you're likely onto something. These visual techniques help you identify patterns, outliers, and possible correlations between the variables. In the process of EDA, you're likely to uncover missing values, outliers, or inconsistencies in your data. This isn't a drawback, it's a feature. Identifying these issues up front can save you from headaches later on when you're knee-deep in the modeling. Once you've conducted a thorough EDA, you'll be better equipped to handle abnormalities in your data. In our next lesson, we'll focus on addressing these issues, such as inputting missing values and treating outliers to prepare your data for advanced analysis. If you're looking for a good library to perform your exploratory data analysis in Python, I highly recommend libraries like Pandas or Matplotlib, which make EDA easier and more effective. The goal of EDA is finding key patterns and themes that will guide your model feature selection, feature engineering, and the data processing to best capture the relationships and trends for accurate predictions. EDA is an iterative process, revisited as new questions come up during modeling. But thorough initial analysis ensures you know the data intricacies so models generalize correctly. Invest time in exploratory data analysis to provide a solid foundation for any data-driven project. Understanding your data up front will not only improve the quality of your analysis, but also guide your decision-making process through the machine learning lifecycle. And far from being machine learning ready. But don't worry, you're probably used to dealing with messy data. And in today's video, we'll dive deep into core data pre-processing techniques that will not only save you time, but also amp your model's performance. When working with structured data, your first hurdle is data cleaning, a crucial aspect that covers missing values. You've got options. Replace an average, delete the record, or leave it be. Your choice should align with your specific use case. Duplicates. Check for them and decide if they are valid. If they aren't, it's time to deduplicate. Outliers. Use anomaly detection techniques like z-scores or the interquartile range to identify and handle outliers. Effective cleaning keeps your models from behaving erratically. Normalization. Bringing everything to scale. Here, we're specifically talking about min-max scaling. It's all about rescaling features to a common range like 0 to 1. This is a cornerstone for many machine learning algorithms. Dimensionality reduction. Less is more. Sometimes fewer variables mean better models. Techniques like principal component analysis and feature selection can help you cut through the noise and focus on what truly matters. Standardization, a different kind of scaling. Unlike min-max scaling, standardization via z-score doesn't confine values to a specific range, which can be advantageous in algorithms where the scale is irrelevant. Finally, some additional techniques worth mentioning. Discretization, turning continuous data into categorical bins, reducing cardinality, but preserving essence. Time series data. Resampling and smoothing are your friends when forecasting is on the menu. Text data. Stemming, lemmatization, and vectorization via TF-IDF get your text data model ready. The Pandas library in Python is your trusty sidekick in this pre-processing journey. It's versatile, user-friendly, making most of these tasks a breeze. I challenge you, grab a dataset, load it into Pandas data frame, and apply what you've learned. Scaling, inputting missing values, binning, and more. Drop me a comment and let me know how it goes. Investing time in pre-processing doesn't just elevate your data, it paves the way for more accurate, reliable machine learning models. So don't skimp on it. crucial machine learning skill that transforms raw data into information features that help models capture key relationships and patterns. Today, we're diving deep into the best practices for feature engineering and introducing some handy techniques you'll use time and time again. Defining features. Defining good features is all about understanding your data and the problem you're trying to solve. Let's say you're predicting customer churn for a subscription service. The frequency of customer interactions could be a strong feature, whereas their account creation date might not be as relevant. Derived features. Derived features can offer extra layers of information. Imagine you're analyzing social media engagement. The ratio of likes to comments could be a more insightful feature than likes or comments alone. Polynomial and nonlinear features. For tasks like predicting the spread of a virus, squared or cubed terms might help your model understand acceleration or deceleration rates. This adds nuance to your model's performance. Time series data. If you're into stock market predictions, rolling averages and leg features can capture trends and seasonality, significantly boosting your model's performance. Text data. Say you're building a spam filter. Techniques like n-gram generation and topic modeling can make your model more effective at catching those pesky spam emails. When you have categorical data, encoding is essential. One-hot encoding is useful for unordered categories like colors or types of cuisine. Labeled encoding is effective for ordinal data like low, medium, and high. Target encoding is great for when you have a lot of categories, commonly used in Kaggle competitions. When diagnosing medical conditions, an interaction feature like age multiplied by cholesterol level could be more telling than either feature alone. Once you've crafted these features, it's crucial to pick the best ones. Techniques like recursive feature elimination can help you pare down your feature set to the most impactful one. Don't forget the scikit-learn library, which provides a ton of these techniques right out of the box. Pandas, NumPy are also your friends here. Remember, investing time in feature engineering can make or break your model's performance. After this movie, I challenge you to pick a dataset and experiment with at least 3 of these feature engineering techniques. Go ahead, start engineering those game-changing features. In this video, we'll provide an overview of supervised learning fundamentals to help you build your skills. The key idea behind supervised learning is using labeled training data to teach models to predict target outcomes. For example, let's say you want to build a model to assess loan default risk. You have historical data on customers, including their financial status, employment status, income, credit history, and of course, whether they defaulted or not. So is this a good fit for supervised learning? In this case, supervised learning makes the most sense. You've labeled historical data you can use to train your model to predict the likelihood of future customers defaulting. Supervised learning shines for prediction tasks. With labeled training data, supervised algorithms uncover relationships between input features like income and the target variable default status to build predictive models. Regression algorithms like linear regression excel at predicting continuous variables such as loan amounts. Classification algorithms like logistic regression and support vector machines handle categorical outcomes like default status. By learning from prior examples, they categorize new data points. Neural networks are universal function approximators, capable of modeling complex, nonlinear relationships for either regression or classification. Their flexibility makes them powerful predictors. Training supervised models is like teaching a student via labeled examples. Given exam questions and answers, they learn how to produce the answers on their own for new questions. The pros of supervised learning include direct optimization of predictive accuracy, thanks to training labels. Models efficiently generalize to make accurate predictions on new data. Downsides include the need for large labeled training sets. Also, models may falsely infer correlations between meaningless inputs and targets, overfitting the data. Use cases like financial forecasting, medical diagnosis, spam detection, object recognition, speech recognition, and most analytical predictions benefit from supervised learning models of labeled examples. In the next video, we will dive deeper into techniques for unlabeled data. But now that you have a good understanding of what supervised learning is and some of the algorithms used in supervised learning, I challenge you to write out a use case for supervised learning. Be sure to list why this model will be beneficial, what data you will use, what will be your predictive variable, what algorithm you will test out. Will you use a neural network or a decision tree? We're finally getting to the fun part of building autonomous machines by selecting and testing different models. So have some fun with your brainstorming. Understanding the strengths of supervised learning will let you leverage it for maximum impact. When target variables exist, supervised models deliver the most accurate forecasts and classifications. You have data on customer purchases, product views, demographics, and more. You want to better understand your customer segments to improve targeting. Should you use supervised or unsupervised learning? In this case, unsupervised learning makes the most sense. You don't have predefined labels or outcomes you're trying to predict. Rather, you want the algorithm to surface insights from the unlabeled data directly. Unsupervised learning finds hidden patterns and relationships in data without any labeling guidance. It's great for segmentation, association analysis, dimensionality reduction, and the discovering of intrinsic clusters. In our e-commerce example, we can leverage clustering algorithms, a key unsupervised technique, to segment customers into common groups based on attributes and behaviors. This provides actionable personas for marketing. K-means clustering is an efficient algorithm that partitions data points into K clusters defined by proximity and centroid centers. New data gets assigned to the nearest cluster. Hierarchical clustering builds a tree diagram, grouping data points by similarity. Clusters merge step by step until reaching a single cluster containing all observations. This reveals structures at different grouping levels. Association learning is useful for product features such as customers who viewed this also viewed that we see on most e-commerce sites. By finding item sets that co-occur frequently, it uncovers accompanying purchase tendencies. The key advantage of unsupervised learning is discovering insights humans wouldn't spot by sifting through huge data sets with no guideposts. Unsupervised models act as data detectives. The downside is the insights are subjective. When working with unsupervised learning, it's as much of an art as it is a science. There are no definitive right or wrong answers, since we lack the labeled outcomes to evaluate against. Interpreting clusters requires qualitative judgment. Use cases like customer segmentation, social network analysis, market basket analysis, and data compression play well into the strengths of unsupervised learning. It shines when exploring unlabeled data. But for prediction tasks or where target outcomes exist, supervised learning is preferable. Labeled data trains supervised models to directly optimize objective predictive accuracy. Understanding when to apply supervised versus unsupervised techniques will help you narrow down which algorithm to use and reduce your time to discovery. Both offer invaluable yet distinct capabilities to harness your data's value. To training AI models compared to supervised and unsupervised techniques. Rather than data examples or unlabeled data, reinforcement learning relies on experience gained through trial and error interactions with an environment. The key idea is that the model or the agent tries different actions within an environment to achieve a goal, receiving rewards or penalties based on the impact of its actions. The agent seeks to maximize cumulative reward through this feedback loop. For example, DeepMind's AlphaGo system mastered the complex game of Go by playing against itself repetitively. Good moves were rewarded with points, while losses taught it better strategies. Over time, it reached superhuman performance entirely through reinforcement experience. Self-driving cars also learn through virtual simulations where the software agents accumulate millions of miles of driving experience, being rewarded for smooth, safe driving. This experience transfers to real-world performance. Reinforcement learning problems are framed as Markov decision processes consisting of states, actions, rewards, and policies. Key algorithms include Monte Carlo methods, which sample many experiences, temporal difference learning, which accounts for future expectations, and deep Q-learning, which approximates the reward function. In traditional reinforcement learning, the reward signal is generated automatically by the system, based on predefined rules and objectives. However, some tasks are too complex or nuanced for fixed reward functions. In addition to traditional reinforcement learning, human feedback adds a valuable dynamic training signal by allowing real people to judge an AI agent's actions and provide subjective rewards or critiques. Looking at OpenAI's chatbot, ChatGPT, we see reinforcement learning from human feedback. This is where the AI agent converses with crowdsourced human trainers. The trainers give real-time feedback on the agent's responses, rating whether they're harmless, helpful, and honest. This aligns the model with human values through reinforcement of ethical dialogue. The agent learns conversing skills that minimize harm and dishonesty, while maximizing usefulness determined by the average human trainer's rating. Reinforcement learning from human feedback is particularly useful for training large language models. The conversational nature of the reinforcement learning allows LLMs to efficiently align with beneficial dialogue behaviors. Other companies like Facebook and Google also use human feedback for reinforcement learning. Showing AI assistants examples of unhelpful or inappropriate responses guides them towards better dialogue. By closing the loop with human judgment in training, reinforcement learning, powered by feedback, better captures the nuances of communications, ethics, and the reasoning compared to fixed rewards. A major benefit of reinforcement learning is the ability to learn optimal behavior independently. However, large amounts of training time in complex environments are required. It also struggles to generalize beyond its domain. Some cases like games, robotics, resource management, and control systems are ideal for reinforcement learning. Whenever an agent can be trained through simulation or real-world experience, it's a powerful approach. Supervised, unsupervised, and reinforcement learning. But you may be wondering, how do these methods lead to exciting applications like computer vision, speech recognition, natural language processing, and more. This is where deep learning comes in. Deep learning is a type of machine learning based on artificial neural networks with multiple layers. The deep refers to the multiple layers in the network. Deep learning methods can be supervised, semi-supervised, or unsupervised. So how does it do its magic? Deep learning models primarily use multi-layered artificial neural networks, such as convolutional neural networks for image recognition or transformers for NLP. But it can get even wilder with deep belief networks and deep Boltzmann machines. In simpler terms, think of deep learning as an assembly line where each layer refines the raw material. In an image recognition task, the first layer might detect edges in an image. The next one identifies shapes by combining these edges. Layer by layer, the network climbs the abstraction ladder until voila, the last layer announces, hey, this is a face. And the coolest part? Deep learning can figure out on its own which features are important at each level. It's a bit like self-driven learning, though you still need some hand-tuning to get it just right. Let's look at some real-world examples. In natural language processing, NLP, deep learning could be useful for things like chatbots, capable of understanding and generating human-like text. All right, let's zoom into our NLP example. This time we're talking about ChatGPT. Ever wonder how ChatGPT can engage in a conversation and answer your questions, or even generate content? Well, that's the magic of deep learning, specifically with the transformer architecture. When it comes to training ChatGPT, the first step involves ingesting a gigantic dataset. The data usually comprises a wide variety of text sources, like websites, books, and more. ChatGPT then uses this data to learn the ins and outs of human language, from basic grammar to complex sentence structure. For a tech deep dive, most of these models are built using frameworks like TensorFlow or PyTorch. ChatGPT, in particular, leverages the transformer architecture. Unlike older architectures like RNNs, transformers excel in handling long-range dependencies in text, making them incredibly efficient for NLP tasks. It's like giving your model a superpower to grasp better context. So how does ChatGPT use transformers to understand your query? It's all about calculating probabilities and weights. If you ask ChatGPT, how does deep learning work? The transformer layers break down the question, assign weights to various words and phrases, and then generate a comprehensive reply that's not just accurate, but also contextually appropriate. Training ChatGPT isn't a set it and forget it. The model requires constant fine-tuning. That includes accounting for nuances like sarcasm, idiomatic expressions, or even handling sensitive topics responsibly. It's an ongoing cycle of training and validation and updates to make sure the bot remains effective and ethical. In the next video, we'll take an even closer look at deep learning and discuss its role in the field of computer vision. Let's talk about another fascinating application of deep learning, computer vision, particularly in self-driving cars. Ever wonder how Tesla's autopilot or Waymo's vehicles can navigate through traffic, recognize pedestrians, and obey road signs? You guessed it, it's deep learning at work. So how do these cars learn to see? They're trained on vast data sets comprised of millions of images and videos captured from various sensors and cameras. These data sets include a multitude of scenarios, pedestrians crossing, different weather conditions, and countless road signs. Popular frameworks for computer vision tasks include OpenCV, TensorFlow, and PyTorch. Neural networks specialized for image data, like convolutional neural networks, are often the go-to architecture. These networks can identify patterns and features in images that are crucial for tasks like object recognition and classification. Let's say a self-driving car approaches a stop sign. The CNN layers process the image, identifying the shapes and edges, and move up the complexity ladder until the network is confident that it is indeed a stop sign. Then, this information is used in real time to instruct the car to stop. The process isn't without its challenges. We're talking about split-second decisions that can be a matter of life and death. The model has to be incredibly accurate, and it needs to be robust enough to handle various conditions: rain, fog, nighttime, you name it. That's why there's a rigorous cycle of testing, validation, and constant updates to ensure not just accuracy, but also safety. All right, friends, let's wrap this up. We've gone on quite a journey in this chapter, from understanding the basics of machine learning all the way to a deep dive into real-world applications like NLP with ChatGPT and computer vision and self-driving cars. In essence, deep learning is the jet fuel that's powering some of the most revolutionary advancements in technology today. Here are some key things to take away with you. Deep learning isn't just some mysterious black box. It's a well-crafted assembly line that builds upon simpler models to achieve stunningly complex results. Whether it's text or images, deep learning models can self-learn the optimal features to focus on in each layer. That's autonomy for you. The tools are there and they're accessible. With frameworks like TensorFlow and PyTorch, you're just a few lines of code away from building your own deep learning model. While we've made huge strides, it's crucial to remember that these models are still a work in progress. They need ongoing fine-tuning and ethical oversight. So what's next? I challenge each of you to dive deeper. Pick an area, whether it's NLP, computer vision, or something else that excites you, and start a project. Hands-on experience is the best way to internalize these concepts. And hey, who knows? You might just build something that changes the game. One of the most essential parts of machine learning and AI: model evaluation and validation. After all, how do you know your model is performing well? That's what we're here to discuss. In supervised learning, we typically split our data into training and test sets. The training set is used to train the model, and the test set is used to evaluate its performance. Let's look at a few common tests that are used. Accuracy measures the ratio of correctly predicted instances compared to the total number of instances. Precision and recall is a test that is useful when classes are imbalanced. F1 score measures the harmonic mean of precision and recall. And finally, ROC-AUC compares the true positive rate against the false positive rate. In unsupervised learning, it's a bit trickier since we don't have labeled data. Instead, we might look at how well the model clusters data or reduces dimensions. Let's take a look at a few common tests used for unsupervised. Silhouette score measures how similar an object is to its own cluster compared to other clusters. The elbow method helps determine the number of clusters. And gap statistics compares the total intercluster variation for different values of K. For reinforcement learning, the model's performance is generally evaluated by letting it interact with an environment and observing how well it maximizes its rewards. Common tests used include total cumulative reward, which shows you the sum of all rewards gathered during an episode. Policy comparison is where you compare the policy derived from the model to a known optimal policy. Because deep learning encapsulates supervised, semi-supervised, or unsupervised models, it can use a variety of techniques as listed above. However, some common metrics include mean absolute error for regression problems, categorical cross-entropy for classification problems, and intersection over union, commonly used in object detection. Understanding how to properly evaluate and validate your model is crucial. Without it, you're flying blind, unsure if your model is actually learning anything useful. Just as we spend time to match the correct model with our data set and use case, be it classification, regression, or NLP, we also want to make sure we match the right test with our model. So, spend the time to get this right. It's just as important as creating the model itself. For your next project, try not to just build a model, but also rigorously evaluate the model. Explore different metrics and even try some cross-validation techniques. You'll be amazed at how much you can learn by critically assessing your model's performance. One of the things I absolutely love about working in AI is that it's truly a team sport. Today, we're going to explore the AI project lifecycle. Today, we're diving into a topic that should be at the forefront of every AI and ML project: ethics and bias. While AI technologies offer unprecedented advantages, they also present ethical dilemmas and can perpetuate or even exacerbate bias if not properly managed. Let's unpack this complex but crucial subject. First up, what do we mean by bias? In the context of AI, bias refers to errors that systematically favor a particular group over another. It's like your algorithm wearing tinted glasses that distort its perception of the world. So, if you're working on a recruitment tool for women in data, and the model unfairly favors one group of people, that's bias, and it can have real-world repercussions. Bias can creep in at various stages. Data bias. This is where your model learns from data. If that data is skewed, your model's predictions will be too. Algorithmic bias. Sometimes the algorithms themselves may inadvertently favor one group. Human bias. Let's not forget that models are built and deployed by humans, who bring their own unconscious bias to the table. This is when that happens. Here are some ways to handle bias in your AI projects. Audit the data. Ensure your data is representative of the population you're studying. Diverse teams. A more diverse team can catch bias that may otherwise go unnoticed. Third-party audits. Sometimes it's beneficial to have an external entity assess your model. Bias isn't the only ethical issue. One of the most pressing ethical issues in AI is model transparency, often referred to as explainable AI. Let's get real for a second. How many of you have used an AI model that spits out predictions without any insight into how it arrived at that conclusion? This black box approach might work fine for recommending a playlist, but when we're talking about healthcare, criminal justice, or even business-critical decisions, understanding the why behind the what becomes crucial. Let's talk about why transparency matters. First, trust. If people don't understand how a model makes decisions, they're less likely to trust it. This lack of trust can be a roadblock in AI adoption. Accountability. In case of errors or controversial outcomes, transparency is key to identifying what went wrong and who or what is responsible. And finally, regulatory compliance. Certain industries require explanations for automated decisions. Transparency isn't just ethical, it's often the law. While we haven't solved all the issues surrounding transparency, here are a few techniques that help. Interpretable models. Some algorithms, like decision trees and linear regression, are inherently easier to understand than, say, deep neural networks. Local explanations. For complex models, techniques like LIME, local interpretable model agnostic explanations, can help explain individual predictions. Feature importance. Tools can rank the features by their importance in making a decision, providing insights into what the model deems relevant. Imagine you're implementing an AI system to match individuals with mentorship opportunities. A transparent model could show that it considers factors like skills, location, career goals, and mutual interests when making a match. This clarity not only builds trust, but also allows for constructive feedback to improve the system further. We'll continue this discussion in the next video, where we will discuss balancing transparency and performance. Is it possible to have both? We'll find out next. Is an important aspect of the ethics and bias problem. But here's the difficult part. Often, the most accurate models are the least interpretable. Is the extra accuracy of a complex model worth the trade-off in transparency? That's a question you'll need to answer based on the specific needs and risks associated with your project. As AI models become more autonomous and sophisticated, there's a growing concern around ensuring these systems align with human values and objectives. This is known as the alignment problem, and it goes beyond just ethics and into the realm of system design and governance. Let's discuss why alignment matters. Safety. As AI models operate in more complex and impactful domains like healthcare or finance, ensuring their actions align with human values is crucial for safety. Ethical outcomes. If a model isn't aligned with human values, it may make decisions that are technically correct, but ethically or morally questionable. User adoption. Systems that align well with human objectives and cultural norms are more likely to be adopted and trusted by end users. Here are a few approaches for ensuring alignment. Value elicitation. This involves explicitly programming the AI system to respect certain values or boundaries. The challenge here is defining those values comprehensively. Inverse reinforcement learning. This is where the model observes human behavior to infer objectives and values, thereby learning what to optimize for. Regular audits and updates. Given that societal values are dynamic, regular check-ins are crucial to ensure ongoing alignment. Let's say you're working on a project aimed at automating social services. If the model inadvertently aligns with the objective of cutting costs at the expense of service quality, you've got an alignment problem. The system needs to balance multiple objectives: cost efficiency, service quality, and ethical considerations to truly align with human interests. As we venture into developing more advanced AI systems, alignment will become increasingly complicated. Researchers are exploring complex but essential questions about long-term value alignment, making sure that as AI evolves, it remains beneficial and safe for humanity. Beyond just being the right thing to do, ethical AI has a business impact. Consumers are more likely to trust and engage with companies that prioritize ethics. Also, avoiding bias can help sidestep public scandals and legal issues. AI ethics is not a side topic. It's integral to responsible development and deployment of AI technologies. Being aware of potential biases and taking steps to mitigate them doesn't just make your AI projects more ethical, it makes them more effective and trustworthy. Let's strive to build AI that not only solves problems, but also does so equitably and responsibly. We've unpacked a lot, from the ABCs of AI to the complexities of the AI project lifecycle. With this space, you're already leagues ahead where you started. But the path to AI mastery is long and diverse. So what's next for you? You see, AI is like a sprawling metropolis. There's something for everyone. Whether it's machine learning ops, data engineering, or AI product management, there's a place that's just right for you. So let's figure out your coordinates on this vast AI map. Was it natural language processing that caught your eye? Or were you fascinated by the classification models and supervised learning? Pinpoint these areas because they're your North Star. For a roadmap tailored just for you, consider these questions. First, your business area. Do you see yourself applying AI in healthcare, automotive, energy, or maybe something totally different? This sets the stage for your journey. Next is the AI lifecycle interest. Was it the rush of deploying the model, the art of the data preprocessing, or the challenge of problem solving that hooked you? Understanding this will help you specialize. Algorithm preference. Did a specific algorithm spark joy for you? Maybe you're the next ensemble method guru or the go-to expert for neural networks. Project joy. This one's all about the feels. Which part of our AI project made you lose track of time? Was it sifting through the data, fine-tuning the algorithm, or maybe the deployment process? If you're drawing a blank on any of these, don't sweat it. Real-world projects have a way of revealing what textbooks can't. So roll up your sleeves and dive into a project. Any project. Watch for those moments when you're so engrossed that you forget to check your phone. These are your clues. Once you've answered these questions, align your learning objectives accordingly. Set SMART goals: specific, measurable, achievable, relevant, and time-bound. Allocate resources like online courses, mentorship, and real-world projects that help you reach these objectives. Remember, AI is a field that rewards the eternally curious and the relentlessly focused. Your personalized learning plan is your ticket to a rewarding career. One where you're not just part of the AI revolution, but you're leading it. So as we wrap up this course, I want to thank you for being an awesome part of this learning community. Stay curious, stay focused, and let's make AI work for us.